Let me just continue the line of reasoning I started in the previous section. And this is exactly the repetition. If we stop our clustering algorithm at this stage, that all distances will be bigger than tau in, or like the tau in is some intermediate state. Then a bunch of particles already clustered in a single device. It's called a jet. It's called a jet. So in this picture, you need the result branching is one. Now we consider in previous lecture we consider that this distribution with respect to maximum KT in branching. What about the previous one? The next to maximum. The next to maximum is, it means that let's consider this area inside tau E, a light little one. And let's imagine that we would like to calculate probability to have one result matching, one red point inside this area. Actually, these two statements are equivalent. Actually, there is only one result splitting, and the second statement. The second hardest splitting, the second from coherent, from the end of clustering algorithm, is smaller than tau in. For example, this one. So this is equivalent statement. Now, what is the probability? For example, if we start from this splitting, then the probability that all potential will be outside of this part of light green area is Sadoko factor which depends on tau in only, on this tau in. So this Sadoko factor includes all resummation of all splittings inside this area. The probability to have splitting is just a Sadoko splitting, yes? The Glock splitting. The Glock splitting general times space and KT should be bigger than tau in here. Now, what is the probability that before the splitting, nothing happens? And again, you need to perform a resummation here. After you resum all possible splittings inside this area and inside this area, you will find that it is simply a ratio of Sadoko factors between Tmax and T. So this is the ratio of probabilities in the whole street and the street below this line T. So quite natural. And here I have this some small gap because the next splitting starts from z squared T. But again, as in previous reasoning, the important region then z goes to 1. So almost to another level of accuracy, I can neglect this z squared here. And if I neglect this z squared here, then all result I talk about is from approximate in potential became exact in potential. So this resummation will be directly lead to this Sadoko factor, and this resummation, if I neglect this pseudo factor from here to tau in, and the splitting. Now, what about if I integrate this probability? I integrate this probability, and again, the same line of reasoning as before. This is a function of tau in. And if I take the derivative with respect to tau in, then it will be probability density function for the second hard splitting. Hardest splitting. These variables, the previous one I called like y3 to 2, 3 jets to 2 jets. And this variable will be y4 to 3, from 4 jets to 3 jets. So, now, let's integrate. But the trick is that it's the same. You should replace the integration variables, change the integration variables to transverse moments and integrate with respect to z, and you obtain the same dispersive functions. They are not cubed. So the total probability is just 4 times this integral. They are gamma cubed. Same. But actually, it's not the end of the story, because we consider only one rod inside branching theory, the leading one, and require that the second hardest splitting has minimum p, has pt smaller than tau in. But in this point, we produce another one parting shower, gluon, for example, gluon one, and we need to take into account also this another rod, not this one. Just let me show you some picture. So, in this consideration, we consider this line, this rod, and this factor is a probability that we do not have hard splitting before this point. And this blue one spherical factor, it is a probability that we do not have hard splitting after this point. And this is the black one is a probability to have hard splitting. But what about this one? About this Cartan shell, which produces a kt which is bigger than tau in. In principle, it can produce kt splitting this kt bigger than tau in, because this is a result ranking. And so we should prohibit it. And how we should prohibit it? We should add the factor which is gluon local factor here, which is start from from starting point of this Cartan shell. This Cartan shell starts from z bar squared t. And this is approximately kt, as you know. This is approximately kt. So what we have here is this one. So this 3-jet rate, it means in z to q bar, for example, you have one, for example, quark jet, and another 2-jet is a gluon jet and quark jet. So 3-jet rate, the total probability is integration of this all of these factors. Pseudo factors, this vertex function, and gluon pseudo factor. So this is the 3-jet. You can generalize this procedure approximately, as I said, approximately by again using something like unity expansion. For example, what's the probability to have double splitting in this row? You just take a unity and represent it is a ratio to pseudo factors. And this pseudo factor is, as we know, this integral of this vertex function. Eliminated. And after that, you expand this exponent with respect to this vertex function. 0 order, first order, second order, and blah blah blah. So this is, we know that it is no result splitting probability. From previous consideration, we can see that if we neglect this gap between t and z squared t, it is one result splitting. these two results split happens not on the main rod, but also this gluon one. So this configuration and this configuration for each rod, this one and this one. So this is a previous result. One of the 2n square of this interval. And for each of them, you should, we should supply pseudo factor for gluon for each subjet, this sub-Parton shower, gluon Parton shower. So I add here gluon pseudo factor after each vertex. And next one, it is this configuration. I have one splitting, one result splitting in quark rod, quark line. This one, so it is the factor times vertex function. And after that, I have one result splitting in gluon rod, this one. So I add the factor times vertex function. And after that, I prohibit the next one, this one, to produce me a result splitting. This is the factor. And the last one is the probability that here should be not gluon splitting, but quark-anti-quark splitting, because it's always possible for quark. But it is already another version. I don't want to talk about it. Okay. Now, let's summarize the result they found. Two-jet rate, product of two spherical factors between q square and maximum of the hard scale to tau in three-jet rate. I did two because we in Z particular bar we have two Parton shower. So the vertex function times pseudo times gluon, it is this side, and another pseudo for this line. So this is a three-jet rate. This is four-jet rate from previous situation. We have here big topology, for example, for gluon production. We have this is previous result, but this is already not one of the two, because one of the two is only for this one, and this one of the two should be for this side and symmetric configuration. But I also need to add this one. So in total, two of this and one of this is actually give you a two. So this is this and this. This line is gluon production and this is quark production. So in any case, we understand actually, it's a long expression. In a few minutes you understand it clearly, absolutely, because it's somehow it's absolutely trivial. But before I explain the structure, let me notice very important note, because I quote for myself a true renormalization. Because we can see the one result splitting here. Here the factor which prohibits splitting before T, which actually take into account the summation all nodes in this area and this area. This is a splitting, and this is a splitting for this area. But if we consider, if we just look on this expression, we can see that it is expression for a single splitting probability for a Parton shower generated this cutoff tau ini. So, in order to, if I always study my KT, the maximum KT distribution using Parton shower which has the cutoff very small. But if I use for my Parton shower generated another cutoff, then it generates me only this point according to this expression. So now let's consider two Parton shower generators, two different ones. One use cutoff gen 1, generator 1. Yes means stands for Parton shower. Parton shower generator 1. This cutoff tau. This is an orange line, the trajectory which is another one, and use this Sudoku and another cutoff which is bigger than this one. This one. So it can generate me only these red points. Now, if we take the result of this generator 1, and select all nodes with KT bigger among all this orange line, we select only nodes with KT bigger than tau inside this area, be generated by Gen 1. Then we obtain the same distributions, the same explicit picture as was generated by generated 1. So you see, that's why I call it renormalization, because I have generate more explicit picture or less explicit picture. Because less explicit picture is generated too. The object generated by this Gen 2 are exclusive in the sense that they are separated at least by distance tau e. These splittings have KT bigger than tau e. But they are completely inclusive with respect to all partons which is closer than tau e. This one, this one, this one, this one. So the object we produce resolved branchings plus infinite number of branchings outside this area. So completely inclusive. So using this Sudoku factor, we just reserve for some time that we can come back and reveal the structure of this branch, like which can do generator 1. Generator 1 can generate all these branches and reveal the real exclusive structure of the radiation inside tau, outside tau e, or inside tau e. So in this area, So the object which we produce, not a simple thing. We produce some object which is separated by cut-off value, but inclusive with respect to all radiation which is closer than tau e. So this is some numerical example in order to convince you that I'm actually correct. I just took the first generated this very small KT cut and select the first splitting in this branching path, the first splitting one. But not maximum value. For example, for this trajectory, probably the maximum value will be the second one. But I took simply the first in branching tree. So this is KT1. And in the result of this Gen 1, I select only those which is inside this KT. And then I obtain the distribution. This is histogram. This is histogram with respect to generator 1. And after that, I simply change the cutoff value and generate this first splitting. Just simply the first in branching tree. The first in branching tree. And I obtain the red curve. So they give the same result. But Gen 1 can generate only these results, please. And Gen 2, but Gen 1 can generate all splittings outside. And by the way, why do we have used generator 2 to generate results splittings? To generate results splittings. Actually, we don't. We can replace this generator 2 by, for example, MGraph and MGevents. So we would like to generate this result splitting by matrix element. Everything matrix element generated like MGraph and MGevents. And everything outside we can use this Parton Shaw. The reason why we should do it, because actually this Gen 2, which is generate very well separated splitting, is very good approximation of a real matrix element. So we should clearly separate the region of applicability of matrix element generated and Parton Shaw generated. The Parton Shaw actually generates everything in single if we consider, just forget about all data, and consider only this vertex function, we will find that this vertex function is actually simply approximation in singular region of the real matrix element squared. And what we can do, so this is this vertex function. Their product is approximation of a real matrix element, probably except because for then we calculate just by hand. We put alpha s fixed, but here we have alpha s fixed on its own this tau prime here, its own pt. It is all alpha s normalized in its own pt, which is different. So this is the only different from a real matrix element. So how we can improve it? We just simply replace all these expressions here and here by exact matrix element. Okay. And what is about these pseudo factors? These pseudo factors, if you can see closer, it's just a product of pseudo factors for every pattern, which is the endpoint is always tau ini, because tau ini is our boundary. Tau ini. At the first argument, it is kt in the place of both of this pattern. So in nodes, there this pattern was produced. For example, for this pattern, this is this kt. So this is tau. For this one, it is tau prime, which is smaller than tau. So everything what we have is just a product of pseudo factors. The second argument of which is tau ini cutoff value, and the first one is kt in the place of the. So for example, this is the total factor, which I call not pseudo factor but pseudo form factor. It's just a product of quark, gluon. Quark is a quark produced in Q squared, so in the primary one. And the gluon and gluon producing some here, or here, and or here. So this tau and tau prime. Tau prime. So the exclusive nature of pattern generated is taken into account by the pseudo-form factor. And pseudo-form factor is just a product of pseudo-form factors for each pattern. The tau e is approximately kt in the place of both of this pattern. Okay. So this is the whole structure. You take matrix element and you multiply it on the product of these pseudo-form factors, which called pseudo-form factors. Now, again, let me summarize. Actually, pseudo-form factor depends on the pattern produced, the identities of the produced particles. So it depends on its identity. Because if you have gluon pseudo-form factors or quark pseudo-form factors or fermion pseudo-form factors, three different pseudo-form factors. But pseudo-form factors doesn't depend on the topology of branch. Because if you can see on the previous picture, it is the same product for any topology. The only argument is only depends on this identity, quark, gluon, and nodal values, tau and tau prime. Tau and tau prime. So it doesn't depend on the topology branch in phi. Invariant. So pseudo-form factor depends on the set of nodal values, which we can find actually using kt class. And each splitting can be presented as a parent-child process. And okay, this is the explanation that the argument of this tau is the nodal value the child was born. So in the place of the okay, and each final state pattern produces contribute as this pseudo-form factor. And the meaning of this pseudo-form factor is exclusion of radiation in the cone of size tau, and all splitting this kt bigger than tau ini. So this is just an exclusive factor which we can by matrix element. Explicit. You need to take into account these Sudoku factors. So the events which are produced by MGraph, it's not a physical one. It's not that we want to take into account. We would like to take into account their experience, the result. So we need to reweight our matrix element result with respect to Sudoku factors, which we can calculate. So this is the algorithm of reweighting. Very simple one. First, we start with the MGraph elementary result. So like matrix. So just select partial identities and multiplicity n according to this probability. The sigma 0 is integrated, regularized cross-section for n parton with certain identity, which the only, of course, if n is big, the only possibility is use Monte-Carlo integration. So, but it is parton which is separated by tau meaning distance, and this is the total probability is 1. Okay, we regenerate and distribute this momentum with respect to what MGraph or MGraph said. So, and for this you use fixed alpha s. Alpha s in this tau e scale, the biggest one, because this is the smallest scale. After that, you run KT-class algorithm to find all the tau. So tau 1 is q squared, tau 2, tau 3, and until tau n minus 1. And all of them, of course, bigger than tau e. After that, identify each parton G. This is the place of birth, this tau. So for each parton, we have this tau. Okay. Now then, calculate the coefficient factor as a product of these Sudoku factors. Just simply, for every parton G, we have tau G to tau e. So this product is the coefficient factor. And after that, calculate the total weight. Total weight is the Sudoku factor times you also need to rescale all alpha, because we use here fixed alpha s, but we would like to use alpha s in these number values. So this quantity is also smaller than 1. So this is smaller than 1, and this is smaller than 1. So the total weight is smaller than 1. If it's smaller than 1, then you can easily reweight all your event, just generate random number between 0 and infinity. And if this error is smaller than this weight, then you accept the configuration you obtain from your Monte-Carlo, your matrix element generator. If not, then repeat procedure starting from step 1 again. So after that, you obtain reweighted events with respect to this weight. Okay. I'm stopping. I already finished it. You have probably more. I didn't prepare one slide, so I can have some time to explain. So you see, these red points, which is generated by our matrix element generator, should be dressed by these patterns from all these patterns which was generated by pattern shower. How we can do it? We can do it using so-called detailed, or Frank Krauss called it truncated pattern shower. So what is truncated pattern shower? This is the whole algorithm. For each pattern shower, we know tau e, tau g. The scale in the place of birth, the initial AT in the place of birth, and in the same time it is starting evolution point for pattern shower in the place of birth. So let's simply generate pattern shower in the direction of each patterns we generate. This initial scale tau e, tau g for each of them. But we generate not simple pattern shower, but detailed pattern shower. And this beta means that then we generate our pattern shower, and if we generate splitting so that KT is bigger than tau in red point. For example, you start from here, blah, 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 you generate here a KT bigger than tau in. Then reload your PS1 in this point. So replace it, maximum value and make the next shot, this one. But do not append this splitting to new branching tree. Simply ignore it. Simply do not, as would be nothing happens. So you trace this trajectory, but only append to your branching tree only branching which happens here, not here. This is truncated partial visit. You generate, and each step depends on previous one. And each split in its point is actually produces its own partial. There's two partners. But if we accidentally produce this result splitting, just ignore it. No, as would be nothing happens. Just jump, perform next jump, but forget about it. So this is a very clever and safe way to remove from part and showers result branchings. So that's all. No, that's the final comment. So this is a matching procedure. Actually, this red point would be generated by matrix element generator. This is my graph. The other black points will be generated by part and shower. And we know that part and shower approximation for the red points is a singular part of the matrix element squares. So for these red points, part and shower pick up the singular structure of the matrix element. So this singular part is smoothly merged with the part and shower because we do it like this. We just simply removed just erased from our part and shower this result splitting. So we need to use this detailed part and shower. And the next point. Only non-singular or less singular which is beyond the level parts have discontinuities here. Because here we use one generator and here we use another generator. So the distribution has some discontinuity, but this is not singular, not important terms. And the last point actually is about inclusive modes, because this inclusive mode was already explained by Johan Hollow. So I just put some point here. The problem actually that every matrix element generator can generate only finite amount of bases here. So the clever way to overcome this difficulty is the inclusive mode. The inclusive mode means actually very, very simple. You do not use, so you generate you generate this matrix element events using cutoff value. But of course, the smallest one, for example, this one, is not coincide with this perfectly. So let's consider the minimum distance, minimum KT, and use this minimum KT for your part and shower generator for beta, for beta part and shower, but only for highest multiplicity sample, only for your the biggest multiplicity events from matrix element generator. Okay, this is a summary of this approach. The total phase space should be, and actually can be, clearly separated by scales out meaning into domains of the applicability of matrix element and part and shower generator. And in fact, this separation also helps to avoid double counting, because you clearly separate which event should be generated by matrix element and which generated by one side, matrix element modification by pseudo-coform factor. We included pseudo-coform factor. They included a summation or the possibility to have some splitter, the inclusive possibility to have spin outside our KT. And on the other side, by implementing weighted partial. So that's why we have seen merging function. And the last point is my personal opinion. Actually, of course, matrix element generator tends to generate more configuration near matrix elements singularity, although they are isolated by cutoff. And this configuration actually acquires the biggest pseudo-Coff suppression because pseudo-Coff factors is smaller than 1. So they are suppressed by pseudo-Coff factors. So more events, more suppression, less events, less suppression. So the CTA procedure is rather effective. And MLM procedure looks less effective because actually then we run KT cluster evaluating without beta. And after that we reject the whole Parton shower. It means that actually we calculate this pseudo-Coff factor on the fly. It's simply Monte Carlo integration. So it's less effective, but of course more universal because it's not stick to the particular branch in algorithm. So I'm finished, but I have one more comment which is important. So I need to draw it on the blackboard. You can try to make some trees. You see, let's imagine that you have matrix element generated. And we know that somehow you can, for each final state, you can introduce branching tree. And this branching tree is generated by Markov process. So, and each Markov process actually depends on its previous stage, from previous step. So you can consider this final state generated by, for example, Markov as a final step of some Markov process. Why? We can simply continue this Markov process. Why? We can just find for example, the closest angle to the partner for each partner and generate its own partner shower inside this cone. Just continue this Markov process, which we know that it only depends on previous step, but not all other steps. Only one previous step. So just we generate it and simply continue this generation by using angular ordering partner shower. Why it would be not correct? Does anybody have any idea? So it's a tricky question. Why we should perform some very strange procedure, just take this final state momentum, perform clusterization, find internal structure or internal KT for each Parton shower in the place of birth, and then generate from this place of birth Parton showers, but not simple Parton showers, but weighted Parton showers. It's not matter. It's so many words. Why we can just simply take this final state and in each one which doesn't contain Parton shower, just completely generate angular ordered Parton shower. Why not? And the reason, the answer is coherence. Because we don't want to consider the only Parton shower, only gluon which is, for example, radiation which is generated by each Parton. But we also would like to take into account the coherent radiation of all pairs, triples, quadruples, of your Partons. We would like to take into account that also all coherent radiation. Now let me draw each. This is this was splitting, the angle is this variable t. Why we can simply continue generation, just put in this point and generate this trajectory from this point. And so this would be generated by matrix element, and this just because it's Markov process, this continuous generation generated by partial Markov process. It is not because we have some events here and here. So the real partial, the more exclusive partial, the trajectory wouldn't be like this. It would be like this and this, this and this, this and this, and after that. So there is some points here and here, which also should be generated. So, for example, between this and this point, we have a coherent radiation in this part. And this part is C. This is Z. This goes to 1. If Z near to 1, it means that 1 minus Z goes to 0. It means that the partner is splitting, is soft, for example. You produce gluon is soft. And if this sub T bigger than this way, it means that we have big T. We have big T means that we have big angle. So actually this area contains soft radiation, large angle radiation. Soft large angle radiation, which is actually coherent radiation. And what we perform? So if we just continue this Markov process from this point, it means that we simply generate in this cone partial, in this cone partial, and in this cone partial. But we don't want to generate only this one, but also the coherent radiation from these two pairs. So the radiation from this one. So we find the place of birth of this partner, and generate partial in this direction. And after that, we find a place of birth for this partner, and start to generate partial from this point. This, all of them, but truncated, because we should ignore the possibility to have results. So, you see, in order to take into account coherent effect, we need to go inside our heart event. We need to know its structure in order to take into account coherent effect. So, this is one notice. The second notice is about that if you just look very abstract at this procedure, you can see that it is somehow not really a clever way. Why? Because we generate here matrix element events, which is actually, as I said, tend to be generated near singularities. I mean, near boundary of the phase space, near singularity. And after that, we multiply it to sort of form factor, which is suppressed. And everything what we do it to have exclusive picture. And after that, we are completed partial. Why? We can leave the events which can be produced by pattern shower as they go, just like this, of the whole pattern shower. Do not perform, but simply subtract from matrix element generated those effects, those events which would be generated by pattern shower, and generate from not the full matrix element event, but only those which is not generated by pattern shower. This is a clever way, and this is exactly, I think, the idea behind this MCH analogic inhibition will be explained to you by Hertz. So just to leave Parton-Shaw alone. So, okay, that's. Any questions?
So how do you estimate the uncertainty in the Parton shower and matching?
It is, I mean, in theory or in practice? In theory, it is something which is all power corrections, like, I would say like this. Tau ini over Q squared. These terms have discontinuities. If you consider that this, if you consider your first section as a function of this maximum AT, you will see that during this mention, these terms have discontinuities from this to this. You only take into account some logarithmic terms like Q squared over tau ini. That this one has discontinuity some power. So this is information. So on the other hand, you need to take tau ini as small as you can, but if you have tau ini as small as you can, then you need to produce more jets for your matrix engineering. But it is in theory, but in practice you just need to vary your